Okay, in this video, we're going to work down through the equilibrium question on the 2019 paper. So it came up in question 11, part B, and it was worth 25 marks. So the first question that we are asked is to write the equilibrium constant for the given equation. So we know when we're writing our Kc that we've got our products over our reactants. And we've got these square brackets to represent concentration at equilibrium in moles per liter. And that concentration is raised to the power of the coefficient in the equation. And the coefficient of each of these products is just 1. And we divide that by the concentration of the reactants raised to their powers, or raised to the power of their equilibrium coefficient. So that is squared. Okay. Now, in the next question, we are asked to calculate the percentage decomposition of 0.2 moles of the BrCl that was placed in a 5-litre container. And we're given the Kc, and we're asked to calculate the percentage decomposition correct to the nearest whole number. So we know when we see an equilibrium calculation that we're going to set up our little table. So we're going to rewrite the equation, little 2 there, and we're going to set up 3 rows. So we're going to have our concentration, our initial concentration in moles per liter. We are going to have the change in the concentration, so we're going to include a row that helps us track the change of concentration, and then we're going to finally have the concentration at equilibrium, and that is also going to be in moles per liter. Okay, so we are told in the question that we start off with 0.2 moles of the BrCl. But that's in 5 litres. So remember, we have to take into account the volume of the container because we want to express our concentration in moles per litre because of the square brackets that we use in the Kc. So what I'm going to do is I'm actually going to divide that by the volume of the container to get it into moles per litre. And that's going to give me an answer of 0.04 moles. So that's my initial concentration of my reactant in moles per litre. Now I also know that initially the concentration of my products is going to be 0. The final piece of information that I'm given in the question is that the value of Kc is equal to 0.22. So I'm just going to leave that down here and we'll come back to it once we've filled in this table. Now, initially looking at this table, it looks like we're not actually given that much information. So what we're going to have to do is introduce an unknown. So I'm going to introduce an unknown in the form of x. So we've practiced a few of these already. Now we need to take into account our ratio before we start adding in our x. So we know that it's a 2 to 1 to 1 ratio. So that means that for every 2 moles of BrCl that we start off with, 1 mole of Br2 is produced and 1 mole of CO2 or Cl2 is produced. So we've got 2 options here for how we include our x. So the first thing we could do is we could say, okay, well, if x amount of my BrCl decomposes into Br2 and Cl2, then going by that reaction equation, half x of Br2 will be produced and half x of Cl2 will be produced. Now, if you're happy to include those halves in the question, then that's absolutely fine. I think that's a little bit too complicated. So what I'm going to do is I'm going to multiply everything by 2 and I'm going to say, okay, so if I have, if I have 2x, that means I'm going to get x of my Br2 and x of my Cl2. So, and remember, the reactant is decomposing, so we put a minus there, and the products are being produced, so we're going to put a plus there. So that means that for every 2x amount or number of moles of my BrCl that decomposes, I've got x moles of Br2 and x moles of Cl2. So that allows me now to finish off this table and to complete the final row. So I know that my concentration of my reactant at equilibrium is 0.04 minus 2x. I know that I've got x amount of my Br2 and I've got x amount of my Cl2. Now what I can do with this is I can fill these concentrations into my Kc that I calculated or that I wrote up at the top. So I've got the concentration of Br2, the concentration of Cl2, divided by the concentration of BrCl, which we have calculated to be 0.04 minus 2x, to be squared. So what we want to do is we want to tidy this up now. We've got an algebraic expression. So this is going to simplify down into a quadratic equation. And I'm going to let you guys do the maths on that. And I'm going to just write the results. So we end up with 0.12x squared plus 0.0352x minus 0.000352 equals to 0. So now what we want to do is solve for x. So what I would recommend that you use is the minus b formula. So you're going to have your x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to again let you guys do the maths on the solving on that, and you should end up with two values for x. So x is equal to 0.303, and remember x is moles per liter, and x is equal to 0.00968, and again that is moles per liter. Now how do we know which one of these is correct? Well, if we go back up to our table, we know that our starting concentration of our reactant was 0.04 moles. Now this 0.3 is greater than 0.04 moles, so we can't have an increase in concentration. If we were to fill this 0.3 into our expression for the concentration of our reactant at equilibrium, we can't have a large number there because that would mean that we end up with a negative moles per liter. So that one, or that answer there, cannot be the correct answer, which means that this is our option. So we've figured out what x is now. What we need to do is go back to the question and see what they want us to do with it. So they've asked us to, let's go back here. They've asked us to calculate the percentage decomposition of that BrCl. So we want to know by how much does that BrCl actually break down. Okay, so what we need to do is we need to calculate the change of the BrCl. So we said that the change is minus 2x. Okay, so let's calculate that 2x. So it's 2 times 0.00968, and that's equal to 0.0194. So what that is saying is that what we have figured out is that 0.0194 moles per liter moles per liter of the BrCl has decomposed. Now to calculate the percentage decomposition, we're going to take the change, or how much has actually been converted. We're going to divide that by the initial concentration and multiply that by 100. So that's going to give us 0.0194 divided by the initial concentration, which we know from our table up above as 0.04, and then we're going to multiply that by 100. That's going to give us an answer of 48.5%, and they did ask us for the nearest whole number, so we'll round that up to 49%. Now that was an awful lot of work for 12 marks, so somewhat unfairly weighted, but it's an excellent question to practice. Now the final part that they asked us, and I might actually just do that over here for you, is for part 3. If we increase the pressure on this equilibrium, the colour intensifies, but it does not change the percentage dissociation of our BrCl. And they're asking you to explain that. So I'm just going to rewrite that equation here. That's BrCl Br2 plus Cl2. Now there's a couple of explanations or a couple of reasons why the percentage dissociation does not change. Well, for the first reason is only temperature will change Kc. Okay? And if Kc changes, then the percentage decomposition will change. That will be affected because the number of moles that are present at equilibrium will be affected. And that's what Kc tells us or helps us to figure out. Now, if we have a look at both sides of the equation, now it is a gaseous equation, so by Le Chatelier's principle, pressure can actually have an effect on the position of equilibrium. Now, if we have a look, we've got two molecules on this side, and we've got two molecules on this side. Two molecules. So the number of molecules on both sides is the same. So that means that the pressure is not going to shift the position of equilibrium. Now, why does the color change or why does the color intensify? Well, what we're doing is because we are decreasing the volume by increasing the pressure, what we're doing is we're actually making the gases more concentrated. And if you think about your Ribena, the more concentrated it is, the more intense the color is. So that's going to intensify the color. So a couple of reasons there. It's only worth 7 marks, so I would give 2 answers just to cover all your bases. So that's the 2019 question.